All right, so Chapter 1, Workplace and Apprenticeship 30. I'm always going to write it WA 30. So that's going to be your course, and you'll see that on the YouTube videos and all that sort of stuff if you need to watch anything like that. But Chapter 1 in Workplace and Apprenticeship Math 30 is linear relations. So why do you think there might be a picture of fuel pumps on this? Anyone?
Fuel consumption.
Okay, fuel consumption. Okay, fuel consumption. What about fuel consumption? What does that have to do with linear relations? Okay, there's a little bit of a caption under there, so you might want to read that, I guess. But fuel consumption vehicles. Okay, so if you have a certain mileage for your vehicle, so let's say your vehicle is pretty good on gas, it gets 30 miles to the gallon. Okay, so let's say that's pretty good. You have an idea, if you know how many gallons your tank is, you have an idea of how far you can go. Does that make sense? If your car can travel 30 miles, and I'll just use miles per gallon, it's common. We use liters and kilometers and all that sort of stuff. But if it gets 30 miles per gallon and you've got 10 gallons, you know right away how far you can go approximately, right? If that's an average. So I'm going to draw a graph here right away. And let's say that after, let's say this is going to be miles over here, and this is going to be gallons over here. So every gallon, 1 gallon of fuel takes you 30 miles. So that's going to be a point that's represented. 1 gallon, 30 miles. 2 gallons, you're going to be able to go approximately what? 60 miles. Very good. 3 gallons is going to take you approximately 90, right? So we're just adding 30 each time, or we're going 3 gallons times 30 miles per gallon gives us, right? So we could do this over and over, and guess what's going to happen? They're going to be something kind of like this. And if you get up to, let's see, 4, 5, 6, 7, this is going to be 7. At 7 gallons, you're going to be able to go approximately 210 miles. Okay? So a graph is helpful, but notice something. I want you to notice something. If you were to connect these points, right? I'm going to do my best here, connect these points. You would have something like a straight line. A straight line. So a linear relation would be a relationship between two quantities that map points out to make a line. Okay? So if the line is curved, if it's a curved line, then it's not a linear relation. If it's a straight line, if the points, when you graph, the relationship between the two quantities, if the points make a straight line, it's a linear relation. So fuel consumption can be thought of in terms of linear relations. Okay, so let's move on here. You guys know about slope, okay? You know about slope. We've learned about slope. So let's just review slope. When we're talking about the slope of a line, okay, let's say we're talking about this line right here. The slope can be calculated by taking the vertical distance, or the change in y values between any 2 points. So this right here is change in y, and dividing that by the corresponding change in x. So for the same 2 points, let's take a look at the change in x. Okay? So if you divide the height by the run, or the lateral distance here, that's rise over run. Remember that? Rise over run. Slope is rise over run, or the change in y over change in x. And if you're given any 2 points on the line, you can simply subtract the y values to get that change in y, and subtract the x values to get the change in x. So the big thing to remember is slope is rise over run. Okay? Got that? Any questions? Rise over run. Now, what does the slope represent in our original example here? Well, if I said to you that the rise between this point right here and this point right here, the rise or the change in y would be 210 minus 0. Right? That's the distance between here and here. And that would be miles. And the run would be 7 minus 0. Guess what that slope is? That is 210 divided by 7, or 30. And look at the units here on our graph. That's miles on top and gallons on the bottom. So guess what? This slope in our linear relation is the rate at which the fuel is consumed. So miles per gallon. Cool, hey? Is all this fitting together? Is this kind of like making sense? Hopefully. Okay, let's move on to the next page here. Okay, so for an example, calculate the slope of a line that has a rise, oh, there's a key term, of 15 meters and a run of 6 meters. So the solution's all worked out for you. You don't have to write anything down, but I'll just highlight sort of how this solution looks here. And of course, we know that slope equals rise over run. So you literally take this number of 15 and divide it by this number, the run, of 6. And as long as they have the same units, that's very important, okay? Same units. Then you can just divide those numbers, and whatever number you get is the slope. Okay? Now, notice in this case, we have meters on top, and we divide by meters on the bottom. So that's why there's no units here. No units. If the units are different, then you have to include the units. Miles per gallon. But meters per meter, they just cancel each other out. They divide each other out, okay? Okay. Okay, this is interesting. This is where it takes it up a level. B says, if the same line is extended to a run of 9 meters, what will be its total rise? Okay. So a run of 6 meters here has a rise of 15 right here. A run of 9 has a rise of, and we don't know. Okay, so now we have to figure out what this is right here. So again, if you know the slope, which we just calculated, you can use your formula to solve for the unknown. So 2.5, if you can't see that in the back, is your slope. The rise is unknown, and the run is 9. How do we solve for rise here? Well, we got to get rise all by itself. So in order to manipulate a math equation, you can always, if it's just two things on either side of the equal sign, like two values, you can always do a cross multiplying, right? Remember, you can cross multiply. So this 9, you can multiply both sides, by 9, and that will eliminate the 9 on the right side. And so you have the rise is 9 times 2.5, which is 22.5. And that's going to be in the same units as the run. Okay? So if you have two pieces of an equation and there's 3 quantities, you can always solve for the third one. Okay? That make sense? Any kind of questions about that? All right. Let's do number 1 together, and then I'll get you to number 2, okay? What's the slope of a wheelchair ramp that has a rise of 3 feet and a run of 21 feet? Okay. Actually, what I'm going to freeze the screen up there, and I'm going to get you to do, we just did one just like this. I'm going to get you to do it on your own, and I will do it in the background, and I'll reveal the answer for you in just a minute, okay? So again, what is the slope when you have a rise of 3 feet and a run of 21 feet? Go ahead. All right, so take a look at the screen there now, and hopefully you got a slope of either 1 over 7 as a fraction, which is totally fine, or 0.14 is okay as mentioned, or you can go 3 or 4 decimal places just to be sure and round it off. So something like this, if that's what you got for a slope, that's great. And notice that the feet, okay, feet divided by feet, there's no units. So you don't have to have units here for this one. Okay? All right. What about number 2? Go ahead and do number 2. See if you can do number 2 on your own. And I'll show you the answer in a moment. All right, take a look on the screen there. So there's my work. Tell me if I'm right, or tell me if I've done something wrong. What I started with, what you always should start with is the formula. M equals rise over run. Now this is a rise, right? The 250. So it goes on the top. And so if you plug in the slope equals 250 centimeters over run, remember the cross multiplying and dividing. You can always go across the equal sign in diagonals, the numbers. And when you do that, they kind of can switch places as well. So if we bring the run up there and the 0.95 down there, this is what we end up with. So I think 263.16 is what. Does that make sense now? Is that okay? Okay. I don't know if anybody else got that, but anyways, good job. Thanks for giving your answer. Anyways, that was just one little thing there. So okay. So rise on top, run on the bottom. Any questions? Maybe the last thing I'll mention here is that I tried to put the units in. See that? So there's no units here. There's centimeters there. So the run is in centimeters. So that's how you can remember that you have to have your units in there. If it doesn't really make sense to you that way, you can just keep your units in the equation, and then if they don't cancel out, you got to leave them in there. Okay?
If they do cancel out, you just write them out.
Well, if things cancel out like in A or in number 1 here, then there's no units. But you see, centimeters doesn't cancel out with anything here. So then you have to have centimeters as part of your answer. If you had the run of just 263.16 without units, don't get full credit. Has to have the units attached, okay? All right, awesome. Now, before we do 3, I'm going to let you do 3 on your own. I'm looking at the time here. Okay, so we're good. Let's do one more example to teach you just a few other terms and do another example here, okay? So working with linear relations, okay, so I mentioned what a linear relation was, and let's just read what it says here. A relationship between two variables, or two quantities, that form a straight line when you plot the values of ordered pairs on a graph. So remember when we went up here on the very first page, remember this? We plotted those points, and because those points fell into a line, we called that a linear, or a line-like relation. If it's curved, if the points form a curved line, not a linear relation. But if they're in a row like that, it's linear. All right. So that's what a linear relation is. Okay. Now, what is a direct linear relation? Here's one. It's a certain type of linear relation. A direct linear relationship has the line. Okay. When you extend that line, it actually goes through the origin of 0, 0. So here's an example of a linear relation. That's a linear relation because all the points that would be on this line form a straight line. But notice that it doesn't, if you extend it, it doesn't go through 0, 0. This over here would be a direct linear relation, like we had in our first example. Because if you extended this line, it would go through the origin. Okay? So this type of question, we'll get into this, but let's say you have someone coming over to your house to do some work on your water heater or something. Okay? So oftentimes they'll say there's a $50 service fee plus $50 per hour or whatever it is. Okay? So that means that as soon as they come, even if it doesn't take them long to fix or assess, you owe $50 as soon as they come in the door. And then every hour after that, $50 gets added on. So it would be kind of like this. Here's the $50 that you owe immediately after they come, and then there would be another $50 every hour that they work. And so that would be a straight line kind of like that. Okay? So that's an indirect linear relation. Indirect. So there's direct and there's indirect. Okay? One other thing, independent variable versus dependent variable. Okay? Now, the independent variable, you probably understand those words, right? If someone is dependent upon someone else, it's kind of like they have to kind of wait around to see what they're doing before they decide what to do, right? If you're really dependent upon your friend, then you kind of like wait to watch and see what they do, and then you kind of like do what they do, right? If you're independent, that means you kind of like do your own thing, you know? I'm going to go do my own thing. I don't care what anybody else does. I'm independent. I can do it. So if we're talking about variables like that, the one that you start with and then the one that you measure, okay, those are the two types. So the one you start with is the independent variable. It kind of like breaks the ground. It kind of takes the first step. And the other variable responds to it. Another name for it is responding variable. Okay? So it's the variable that depends upon what the other variable does. Now, in this example, in the very first example, the mileage, basically the independent variable would be how many gallons you have, right? Because every car, you could start with a certain number of gallons. And then you drive it, and you see how far you go. Does that make sense? So the independent variable would be down here on the horizontal part of the graph, and the dependent variable is on the vertical part of the graph. So if I put 5 gallons in your car and 5 gallons in your car, and I want to see who has the best mileage, then you both drive until you run out of gas. And then we measure how far you went, and I measure how far you went, and I write those down. So independent variable is the amount of fuel. The dependent variable is how far you can go on that fuel. Does that make sense? Okay. So other relationships would be like time of year and snowfall, right? You always kind of start with the time of year, like, oh, January, okay, January, let's measure the snowfall, right? July, let's measure the snowfall, hopefully 0, right? So you can kind of get an idea of which is independent, which is dependent. Sometimes it's tough to tell, and sometimes, honestly, it doesn't really matter. Like if you're saying, mass versus height or something of a certain animal or something. Well, what comes first? I mean, I don't know. Do you measure do you take a certain mass and measure the height, or what? Like they're kind of like almost equal, right? You got to measure both of them. It's like, I don't know. So sometimes it doesn't really matter. Sometimes it's hard to tell, but sometimes it's easy to tell. So that's the explanation of that. Okay, where was I? Looked like I missed something here. Okay, so the bell's going to ring pretty soon. So let's just go over this example, and then we'll call this a lesson, okay, for today. So Kalinda babysits on weekends and charges $12.50 an hour. The following table of values shows her earnings based on the number of hours she babysits. Okay, so take the number of hours, and then you calculate the earnings, right? That's what you guys do, right? Oh, what did you work this week? Oh, I worked $50. No, you worked... let's just make it simple. I worked 5 hours, and I earned $50. Okay, so $10 an hour. So you start with the number of hours you worked, and then you can calculate how much you earn. Now you can go backwards too, but I think it makes sense that this is the independent variable over here. This is the dependent variable. Okay, for A. Use the data to graph the data. Should you connect the points on the graph? That's interesting. The question about connecting, I think we talked about this in 20. Now, if you get paid for partial hours, which most of you probably do, you could probably connect. If you only get paid for every full hour you work, then you wouldn't connect the dots. Because if you worked 1 hour, you get paid a certain amount, but you wouldn't get paid any more until you worked a second full hour. Let's say that was the arrangement. Then you wouldn't connect the dots. Because an hour and 10 minutes, an hour and a half, an hour and 50 minutes, what you get paid wouldn't change. Now, that doesn't really make sense, right? But so if you're earning something, usually you can connect the dots, right? Okay? So if the points in between make sense, and they kind of go along with the data, then you can connect the dots. If it's mass of people versus height, and I say I'm going to take your mass and your height, and then your mass and your height, there's really no connection between you two, right? So in that case, if you were graphing those points, you wouldn't connect them. Because A, there's no Caleb Nathan hybrid person in the middle that would automatically be the exact average of your weights and the exact average of your heights. That makes, you know what I mean? So it's not reasonable, so you wouldn't connect the points. Make sense? That would be a very scary proposition, by the way. I'm having trouble even thinking of it right now. A human that has the combination of you two is like, whoa. I'm kidding. I'm just kidding. Okay. Oh yes, that would be a super cool human. It would be. Yeah. We'll go with that one. Okay. Yeah. All right. Is it a straight line? Is this a linear relation? Yes. Is it a direct linear relation? Yes. It goes through 0, 0. Okay. Very good. what is her hourly rate? That's the money per hour. How can we calculate that?
Give us a question.
Sorry, what'd you say?
Says 1250.
Why? Why is it? Okay, you look at the answer. Fine.
No, it's
What does it mean?
It's in the question. She makes
Oh, it's in the question?
12.50 an hour.
Okay, fine, whatever. Where does 1250 fit on this graph then?
It would be in the 1 hour. Should be like after 1 hour of work. You get
Okay.
12.50.
So after 1 hour of work should be 1250. Okay. Where else is 1250 in this graph? Sorry?
On the Y axis.
Think about the mileage of the car. 30 miles per gallon. What was that? On that graph. Do you remember?
12.50 per hour.
Okay, so 1250 per hour. So that means that for every hour you work, you get 1250 more, right? 1250 per hour. What does dollars per hour?
Oh, that's her rate.
That's the rate, yes, but where on the what on the graph is 1250 per hour?
What-
Dollars per hour.
Oh, were we set up for X and Y?
It starts with an S and ends with a
Slope.
lope. Okay, the slope. Is the slope 1250 per hour? 1250 over 1? Well, let's just... Sorry?
I told you that.
You told me what?
You did not.
You did not say slope. You did not. Nice try. Okay, so what is 6 hours? Oh, that's tough to tell, right? 78 something, really, right? 77, 78. So if you did 78 divided by 6, what do you get? I mean, we're not exact here, but actually we can go back to the table, fine. Okay, so 75. So 75 divided by 6 is 75 divided by 6 is, boom, 1250.
Oh.
Okay, so that's the slope of the line. Okay, that was painful, but we got it. So here's the slope. Take the difference between any 2 points and the difference between any 2 points this way. You divide them, you get the slope, and that actually turns out to be the same as the rate. Okay. Okay, so we're going to stop there for this lesson. Your assignment is to finish 1 to 3, if you didn't get those done, and to also do, let's see, well, because I'm not giving you a whole bunch of time here to do this, when does this class end? Yeah, about 4 minutes or so. So I tell you what, why don't you do number 4 and 5, please, for tomorrow. So do number 4 now, see if you can get number 5 done as well.
So 4 done, 5 done.
Yeah, 4 and 5. That's your goal. Okay, and we'll pick her up tomorrow. We'll pick up tomorrow right here working with partial variation. Okay, good job.